Hi friends, so in this new video I will talk about ultra wideband antennas. Okay, ultra wideband characteristic, when we can say that we have real ultra wideband antennas. Okay, so in this video I will talk about some definitions that we can use for ultra wideband antennas. I will talk about norms and standard of ultra wideband antennas. I will talk about ultra standard ultra wideband characteristic, and I will talk also about techniques and some examples that we can use to have an ultra wideband antennas or horizon antennas. Okay, so the plan that we can use for this presentation. So in the first axis I will talk about some definitions. In the second axis I will talk about ultra wideband standard or norms that we can use for ultra wideband antennas. And in the last axis I will talk about methods of ultra wideband characteristic and some examples. Okay, so the first definition is the return loss, or S11, or reflection coefficient. So what does mean reflection coefficient? So if we assume that we have a source of power with a coaxial cable that's related between antennas and source. So here we have incident wave that come from source toward the antenna. So we have a reflected power or wave and input of our antenna. So we have a transmitted power and we have a reflected power. So the return loss is the ratio between the reflected wave and incident wave, or reflected power and incident power. Okay, so return loss or coefficient of reflection is the ratio between reflected wave and incident wave. So this parameter we can use it, or we use it a lot of to know the ultra wideband characteristic of antennas or horizon antennas or any microwave devices. Okay, so bandwidth of antenna, how we can determine the bandwidth of antenna. So to determine this bandwidth, we need to represent return loss in function of frequency. Okay, so we have return loss in decibel in function of frequency. So to talk about bandwidth of antennas, we need to know if we have a return loss inferior of minus 10 decibel. Okay, so if we have a return loss inferior to minus 10 decibel, so we can talk about the bandwidth of our array antennas. So for this example, the bandwidth of our antennas is between f1 and f2. Okay, so this is the bandwidth of our antenna. Okay, the bandwidth is between f1 and f2. fc is the center frequency, okay, of this antenna. It's the center frequency. We will talk about center frequency in the next. Okay, so the bandwidth of antenna is determined by the return loss in 10 decibel. Okay, so this is the method used to know the bandwidth of any antennas or arrays antennas or coupler or filters. Okay, we need to represent the return loss in function of frequency, and we take the value at 10 decibel. So for antennas we talk about 10 decibel, but for other examples we can find 6 decibel, we can find 15 decibel. Okay, it depends on application, but the popular value is 10 decibel. Okay, so bandwidth of antennas. The first, so I see that the bandwidth of antenna is equal to frequency to my frequency 1 to know the value, the exact value of our antennas or arrays antennas. So, for example, if we have 8 gigahertz for f2 and 4 gigahertz for f1, so the bandwidth of our antenna is 8.4 equal 4 gigahertz. Okay, 4 gigahertz. So we can find that in other examples that we can talk about fractional bandwidth. Instead of bandwidth of antenna, we talk about fractional bandwidth in percent. Okay, in percent. Some example to cannot find the bandwidth in gigahertz, but we can find fractional bandwidth in percent. So to determine this parameter, so we take f2, the frequency 2, minus frequency 1 divided by center frequency. Okay, multiply by 100 to find our fractional bandwidth in percent. Okay, so for the center frequency fc we can determine it by f1 plus f2 divided by 2. Okay, so this is the center frequency of our antenna or our microwave devices. Okay, f1 plus f2 divided by 2 can give us the center frequency of our devices or microwave devices. Okay, and when we find the center frequency, we can find the fractional bandwidth in percent. Okay, f1 divided by fc and multiply by 100 to find the value in percent. So in the second axis we talk about ultra wideband standard or norms. Okay, so from FCC, Federal Communication Commission, so we can find that, or we can talk about ultra wideband characteristic if we have an antenna or array antenna or other equipments. So if we have a bandwidth, okay, a bandwidth superior or equal 500 megahertz. Okay, 500 megahertz. If I talk about bandwidth, if I talk about fractional bandwidth, so we need to find a fractional bandwidth superior or equal 20%. Okay, in fractional bandwidth we need to have fractional bandwidth superior or equal 20%. Okay, so the first condition. The second condition, this bandwidth must be belong to 3.1 gigahertz and 10.6 gigahertz. Okay, we need to have a bandwidth superior or equal 500 megahertz, and this bandwidth is belong to 3.1 gigahertz and 10.6 gigahertz. Okay, so I will give you example for this to understand these conditions. Okay, so that's for in general. In Europe, or instead to talk about bandwidth superior or equal 500 megahertz, so we talk about just 215 megahertz. Okay, 215 megahertz. Okay, a bandwidth superior or equal 250 megahertz, and this bandwidth belong to 3.1 gigahertz and 10.6 gigahertz. So in Europe we can talk about ultra wideband characteristic of any microwave devices. Okay, so this is the conditions that fixed by FCC, the Federal Communication Commission. Okay, so here we have an example of ultra wideband antennas. So if we take this antennas, we have return loss in decibel and we have frequency in gigahertz. Okay, so if we go toward 110 decibel here, okay, 110 decibel, we can find that we have a return loss is inferior to 110 decibel between this point, I think 3.2 gigahertz. Okay, so the return loss starts from 110 decibel in 3.4 or 2 gigahertz toward this frequency here. Okay, I think that 9.2 or 3 gigahertz. So here I have a bandwidth greater than 500 megahertz. So the bandwidth of this antenna is I think I have 5 gigahertz. Okay, 5 gigahertz. So 3.2 toward 9.2. So I think yes, we have 5 or 6 gigahertz in bandwidth, and this bandwidth is below 3.1 gigahertz and 10.6 gigahertz. So this antenna has a bandwidth greater than 500 megahertz, and this bandwidth, okay, this bandwidth is below to 3 gigahertz and 10.6 gigahertz. So we can talk about ultra wideband characteristic of this antenna. This antenna is verified ultra wideband characteristic fixed by FCC. Okay, so this is the first example. If we take another example here, so we have another antennas. Okay, we have the return loss in decibel in function of frequency in hertz. Okay, so this antenna has a return loss moins 10 decibel here from 401 megahertz to 406 megahertz. So this antenna is not ultra wideband. We cannot talk about ultra wideband characteristic for these antennas. Why? Because the bandwidth of these antennas at 110 decibel is inferior to 500 megahertz. So the bandwidth here just, so if we make a difference between 406 megahertz and 401 megahertz, we can find just 5 megahertz. We have just 5 megahertz for these antennas, and so in this characteristic, in this bandwidth does not respect ultra wideband characteristics. So we cannot go to talk about the second condition of this the 3.1 gigahertz and 10.6 gigahertz. So we cannot talk about ultra wideband characteristic. Okay, so other things, so we will talk about narrow band and ultra wideband. Narrow band and ultra wideband, the difference between narrow band and ultra wideband characteristics. So in figure 1 we talk about temporal representation of a signal in red color ultra wideband signal, and in blue color or narrow band signal. Okay, so here we have a power spectral density in temporal representation. Okay, so here we can observe that the signal has a short time for ultra wideband characteristic, a red color. We have a short time. We can send our signal in a short time instead of the signal in narrow band. Yes, it has a big time. Okay, so if we make comparison in terms of time, so we can find that the ultra wideband characteristic has a short time in sending. Okay, so in figure 2 we have a frequency representation. Okay, the frequency representation. So for ultra wideband characteristic, we can observe in red color that we have ultra wideband. Okay, ultra wideband. Okay, so if we make comparison with narrow band, so we have just small bandwidth for narrow band. So if we make comparison also in power spectral density, we can observe that narrow band has a big power spectral density, but for ultra wideband we have a small power spectral density. This is the advantage of ultra wideband characteristics. So we have ultra wideband, and a small power spectral density. Okay, so this is the difference between narrow band and ultra wideband and temporal representation and frequency representation. So some advantage of ultra wideband characteristics. So the first advantage is the high data transfer rate. So because we have ultra wideband, okay, so this can give us a high data transfer in comparison with narrow band. Also, in terms of spectral power density, we have a low spectral density in comparison with narrow band. We can talk about also of lower cost and low complexity and other advantage. So the last axis, so the methods that we can use to find ultra wideband characteristic of antennas and examples are some examples. So the first method that we can use to find ultra wideband characteristic, we have the partial ground plan, okay, and the second method is the multi-layer antennas, okay. For the first case, partial ground plan technique. Okay, so here in the left we have a single patch antenna. So in the left we have the top view, we have the radiating element, circular radiating element with a feed line. Okay, the feed line here we can find the part of excitation. So this is the top view, and the bottom view we have the partial ground plane in black color. Okay, so the sample antennas we have a total ground plan. Okay, but to have ultra wideband characteristic we need to work with a partial ground plan. Okay, so here we have a partial ground plan in bottom view, and we have the radiating element and feed line to feed the radiating element in black color in top view. So in the right we have the return loss in function of frequency. So for this antenna we have a frequency between 4.1 gigahertz toward 6.4 gigahertz. So we can talk about that. We have original loss inferior to 110 decibel from 4.1 gigahertz to 6.2 gigahertz to 6.2 gigahertz. So we have a bandwidth superior to 5 megahertz, and this bandwidth is belong to 3.1 toward 10.6 gigahertz. So here we verified the stock condition of the FCC norms. Okay. Other example here we have a linear array antenna. So we have here four radiating element linear array antenna, and in top view and in the bottom view we have a partial ground plan in gray color. Okay, so for this linear array antenna we can find ultra wideband characteristic, and here we have the return loss of this array antennas in function of frequency. So here if we look the return loss we at 110 decibels, so we have the bandwidth is from 3.5 or 6 or 7 gigahertz toward 6.2 or 3 gigahertz. So here we have a bandwidth greater than 500 megahertz, and this bandwidth is belong to 3.1 and 10.6 gigahertz. So in this antenna we verified the condition of the FCC of ultra wideband characteristic. So here we have a return loss comparison between CSTR software and HFSS software. So this is two software that we can use to conceive antennas. These popular software are able to work in antennas or array antennas or any microwave devices. The last example here is a planar array antenna. Okay, so here in top view we have 8 radiating element, rectangular radiating element with divider power here. Okay, principal divider power, and here we have the parts of excitation. So in the top view we have in black color the radiating elements, and in bottom view we have the partial ground plan in gray color. Okay, so for this example also we have ultra wideband characteristic here. If we look well the return loss comparison between HFSS and CST, we can observe that we have a return loss inferior to 110 decibel from 3.5 GHz toward 9 GHz. So here also we've verified the condition of ultra wideband characteristic. We have a bandwidth greater than 500 MHz, and this bandwidth is belong to 3.1 GHz and 10.6 GHz. So here the second technique used to find ultra wideband characteristic, we talk about multilayer technique. So in French we talk about multicouche antenne multicouche. Okay, en français in French we talk about antenne multicouche multilayer technique. So here we have the principal antenna. Okay, so we have the substrate in green color, and in orange color we have the radiating elements. So here we have a lot of substrates, so we talk about multi-layer, and we have radiating elements. Okay, and we have ground plane, okay, between each substrate. Okay, so this technique is used also to find ultra wideband characteristics. So here we have a return loss in function of frequency, so we can find that we have ultra wideband characteristic. Why? Because we have a return loss minor than 110 decibel from 2 GHz toward 12 GHz. Okay, and this bandwidth is below 3.1 and 10.6 GHz. So we can talk about ultra wideband antenna. Okay, so we have another example here. We have a multi-layer antenna. So we have here the substrate in the bottom, we have the substrate in black color, we have the feed line used to feed the radiating element in green color, and we have a ground plane between these two substrates, and we have a radiating element in green color. Okay, so in ground plane we use two slots in form of U. Okay, U letter. Okay, so this is a technique used to find ultra wideband characteristic. I talk about multi-layer antenna. Also, this single antenna, patch antenna, is ultra wideband. Why? Because we have a return loss inferior to 110 decibel from 4 GHz toward 8 GHz or 8.2 or 3 GHz. So also this antenna is ultra wideband. Why? Because it has a bandwidth greater than 500 megahertz, and this bandwidth is belong to 3.1 gigahertz and 10.6 gigahertz. Okay, so I represent the popular techniques that we can use to find ultra wideband characteristic for antennas. Okay, so I finished this presentation. If you have any question, any remarks, anything that not clear, you can contact us in our YouTube channel, okay, by comments, or you can contact us in our Facebook account. Okay, so see you in other video.